Today, I will be discussing a study on the motor basis for misophonia. Misophonia, literally meaning hatred of sounds, is a common disorder in which ordinary, everyday sounds cause intense, negative, emotional responses in sufferers, including anger, anxiety, irritation, and disgust. This may also lead to the fight or flight response, which is characterized by violent rage or desire to escape the situation. Spontaneous mimicry may also occur, which is characterized by the sufferer unconsciously mimicking the sound that is triggering them. Trigger sounds are primarily caused by orofacial movements such as eating, drinking, or breathing. Examples include chewing, sucking, lip smacking, swallowing, or slurping sounds, in addition to other common everyday sounds at normal volume. The reason for these intense responses to such common sounds is unknown, and the ordinary nature of the sounds makes this disorder much more intense for sufferers and their families. It can lead to social isolation and even suicide. These sounds are triggering to misophonia sufferers when they're produced by other people, however, not when they're produced by the sufferer themselves. Although sounds are the most upsetting to sufferers, the same feelings of distress are experienced by sufferers when watching silent videos and images of eating and chewing. This means that the action of the trigger person may be just as significant as the sound. So there should be a focus on the movements associated with the sound rather than just the sound itself. The brain areas and mechanisms that are hyperactive in sufferers include the anterior insula, which is a small region of the cerebral cortex that plays a role in regulating feelings, the ventral premotor cortex, which receives signals from the auditory and visual cortex, and specifically the connectivity mechanisms between the auditory and visual cortex and the ventral premotor cortex, and the mirror neuron system within the ventral premotor cortex, which responds to the actions of others. The mirror neuron system is the set of neurons that was discovered in monkeys that fire when the monkey performs an action, but also when the monkey sees another individual performing that same action. This is why it causes spontaneous mimicry or automatic imitation in misophonia sufferers. This happens when subjects mimic the action of the person making the trigger sound due to loss of control, invasion of personal space, or interference with current goals or actions. This is why people experience distress when seeing the action that the sound is coming from, as well as the sound itself. This mimicry is used as an unconscious coping strategy because of the mirror system activation. So, in sufferers, trigger stimuli activate the same part of the motor cortex that is activated during the generation of these same stimuli. The research objectives of this study were focused on providing a new perspective that focuses on the action of the person producing the trigger sounds rather than the sounds themselves. In the Journal of Neuroscience article, authors Kumar, Dhirendra, and Irfanian state that sounds in this new perspective are only a medium via which the action of the triggering person is mirrored onto the listener. This research is crucial for expansion of treatment methods and therapies for misophonia, because the authors state that instead of focusing on sounds, which many existing therapies do, effective therapies should target the brain representation of movement. The methods section of this experiment included 17 subjects with misophonia and 20 control subjects, which were recruited for participation in the study. All of the subjects took several questionnaire assessments for misophonia. And based on assessment results for the Misophonia Amsterdam questionnaire, subjects with misophonia were ensured to have scored a 10 or higher on this questionnaire. This indicated that they were in the moderate to severe range of misophonia. None of the random control participants were identified to score within this range of the test, therefore scoring within the normal range. On a questionnaire designed in the laboratory that conducted the study, the misophonia group scored higher with an average of 42.6 on the questionnaire compared to controls who scored an average of 17.6, with a lower score indicating a more normal response. The fMRI resting rate was recorded in misophonia sufferers and control subjects. fMRI is a non-invasive and safe way to measure and map brain activity. This experiment consisted of two tests, the RS fMRI test and the sound evoked fMRI test. The RS fMRI test consisted of 10 minutes of data being collected while participants kept their eyes open. An eye tracker checked whether or not participants were conforming to this instruction. Psychologic measurements, heart rate, and respiration were monitored using a pulse oximeter and respiration belt. For the sound evoked fMRI testing, there were 3 categories of sounds played to the participants. The first one was trigger sounds, which were expected to cause a reaction in individuals with misophonia. An example would be chewing or eating sounds. The second category was aversive sounds, which were expected to cause both groups to feel discomfort. So, an example of this would be an infant crying. And the third category was neutral sounds, which was not expected to cause a reaction in either group, such as a white noise. The results of this study showed that misophonia sufferers displayed stronger fMRI connectivity between the auditory and visual cortex and the ventral premotor cortex responsible for orofacial movements. Also, stronger functional connectivity between auditory cortex and the orofacial motor area during sound perception in general. There was also stronger activation of the orofacial motor area in response to trigger sounds, which shows that the activation of this orofacial motor area increased in proportion to the distress that the individual was experiencing while listening to the trigger sounds. They also displayed hyperactivity in the anterior insula in response to trigger sounds, which is significant because the anterior insula has stronger resting state connectivity to the cerebellum, which is known to be involved in social cognition in general and mirroring of actions of others in particular. They also displayed spontaneous fluctuations in the auditory and visual cortex. The results on the right are cluster corrected with a p-value of 0.001. So the top row shows seed regions, the middle 2 rows show the connectivity pattern on the sagittal and coronal sections of the image, and the bottom row shows bar plots of the mean connectivity strength in the 2 groups, the misophonia and control groups. The misophonia group also showed no difference in the auditory cortex responses when compared to the control group. The results of the study highlight a specific model that misophonia sufferers experience hypermirroring of the orofacial actions of others. So, in other words, misophonia sufferers experience unusual activity in the parts of the motor systems involved in producing these sounds. This model emphasizes the role of the motor system in misophonia. So, higher order motor cortex is involved, which indicates a complex role of the motor system. The Neuroscience Journal article also stated that although neuroimaging studies have identified a brain network underlying misophonia, the question of why such innocuous sounds cause distress and hyperactivity in the brain regions remains unanswered. Discussion. The journal states putting together results of resting state connectivity, sound evoked functional connectivity, and activation, our data strongly support the hypothesis that misophonia is characterized by aberrant functioning of the mirror neuron system, which mirrors the action of the trigger person represented by sounds. Misophonia is characterized by increased functional connectivity between the orofacial motor area and both the auditory and visual cortex in a resting state as well as in response to all types of sound. It's also characterized by increased resting state functional connectivity between the ventral premotor cortex containing orofacial motor area and insula in the resting state. This counters the misconception that misophonia sufferers have differences in the auditory cortex itself, as there was no difference from the control group in the activation of the auditory cortex to triggers and other sounds. Sounds produced by others only represent the actions that produce them. To critique, there were some limitations to this study. The first limitation being that the demonstration of mirror neurons is extremely difficult to do on humans because it requires invasive single neuron recording. A future study may consider conducting indirect single neuron recordings on humans in a less invasive way. Another limitation was that there were reports that misophonia sufferers have triggers that are non-human, such as sounds that come from animals or machines. This could be applied to a further study using other trigger sounds or movements that are non human.